Hi, and welcome to this second video on the binomial distribution from the stats section of the A-level maths course. The previous video we looked at the criteria that a random variable needs to have to be classed as binomial and how we can use it, and we looked at all the theory behind it. Let's now just crack on and have a look at how we're actually physically going to use it. So we're going to have to calculate probabilities for specific values, for values in a given range, and also we'll have a look at stats functions on the calculator. So here we go. So straight away we've got a set where we're told that x is binomial. We've got 10 trials as indicated by that parameter there, and we've got a probability of success which is 0.4. So it's those two values that are parameters for the distribution, and straight away we know if p is 0.4, success is 0.4, that means failure is going to be 0.6, and those are all the bits that we talked about in the previous video. So let's just crack on straight away and have a look at how we can go about finding these. Now I'm going to do all of these kind of old school, if you will, to begin with, until the new specification 2017 calculators, you had to kind of do the number crunching by hand, so to speak, whereas now we've got a function on the calculators that'll do a lot of it for us. But we'll do it old school to begin with so we understand kind of the theory behind it, and then we'll get into how we can use the calculators a little bit later on. So here we go. So probability that x equals 7. So what we've got is 10 trials, 7 successes. So what we need is the number of combinations. That's our 10C7. We then need the number of successes, which is 0.4 to the power 7. And then we need the number of failures, which is 0.6 to the power of 3. So that's how we're going to cobble together our calculation. And then it's just a case of whack that into the calculator, and we end up with our probability. So 0.04247. Hopefully we're all happy that that's fairly simple, straightforward. It's just a case of plugging numbers into the formula and then stick them in the calculator. Right, probability that x is equal less than 2. This one's going to get a little bit more complicated because probability x equal less than 2 actually involves probability that x is 0, probability x equals 1, plus the probability x equals 2. So we've got 3 separate bits we've got to calculate. And so there we go. That one is the probability that x equals 0. Now you'll notice from this, I always go for it in terms of the 3 bits, because with my students I like to reinforce the fact we've got 3 parts to it. Combinations, successes, failures. There they are. Combinations, successes, failures. But if you have a look at that bit there, 10C0, that's got a value of 1. 0.4 to the power of 0, because we've got no successes. That's 1 as well. So we could just write this as 0.6 to the power 10. But I always kind of tend to encourage that, so we're thinking about combinations, successes, failures. So that's probability that x equals 0. That bit is probability that x equals 1. And that bit there is probability that x equals 2. Again, combinations, successes, failures. And put them all together into the calculator, and it spits out a value of 0.1672. Right, on we go. So we've got those first two. And then for the last one, we've got probability that x is greater than 2. This one is the one that's slightly more problematic, needs a bit more thought, because you'll realise straight away that if I've got to include all the ones that are greater than 2, that's all of these, so x equals 3, x equals 4, x equals 5, all the way up to x equals 10, which is a lot of number crunching, a lot of button pushing on the calculator. But there is a much, much quicker way of doing this, which would be to have a look at what we already did in part B, which is where we calculate the probability x equals less than 2, and hopefully you've already clocked what's going to happen here, in that if I take all of my possible values for my random variable from x equals 0 all the way up to x equals 10, then what I've got is that one which I already calculated. The one I'm being asked to calculate is that one in blue. So if we know that all of these things add to 1, all I've got to do to get the blue bit here, all I need to do is 1 minus this one here, which is what I already had. So the probability that x is greater than 2, that's strictly greater than 2, so the first one would be 3, would be 1 minus the probability that x is equal less than 2. That value we've already got, so we've just got to turn it around, which is 1 minus 0.1672, which is 0.8328, and there we go. So being able to do that 1 minus trick makes the whole calculation a whole lot more simple, and again, depending on which calculator you've got, this calculation, the kind of the greater than one, you can do on the CG50 calculator, the big graphical one, whereas if you've got the FX991, the class whiz, it will only set it up as a less than, so you'd still need to, you'd still need to do the 1 minus trick. But again, we'll talk a little bit more about the calculators later on. So here we go. So what we've got now is a question that's put into a context. So we've got a study showed 31% of the school children were getting the required amount of sleep per night, and we take a random sample of 20 students. So the first thing is explain why binomial is the appropriate model to use. And now on the new specifications, we're getting a lot more of this kind of question where you've got to justify your choice of model. So why is it a binomial is appropriate? Well, we've got to go back to the definition of a binomial and the characteristics of a binomial, which is the fact that we've got a fixed number of trials, in this case a fixed number of people and sample. We've got the probability is fixed and it's independent. So we've got this kind of 31% of school children, so that's taken from a much, much larger group. So the probability of any given child from that sample is 0.31. And we've got two outcomes, success and failure. So we've got to link those back, and we've got to make sure that we're describing them in terms of the context. So success, enough sleep, failure, not enough sleep. So what we've got is a binomial, and we can describe it as being x, our random variable, is distributed binomially with n being 20 and p being 0.31. And so on we go to part B, and part B is requiring us to work out the probability that x is less than 4. And note again, it's strictly less than 4. So we've got to think very carefully about precisely which values we're including here, and that's going to be x equals 0, 1, 2 and 3, but we're not including x equal to 4. And note as well that this thing here, x less than 4, we could just as easily describe this as probability that x is equal to or less than 3. Because it's discrete, x equals less than 4 is exactly the same as equal to or less than 3. So we've got all those to do, so let's just work those out. We're going to write them out longhand, so here we go. So there's our probability that x is 0, so that's 20 failures effectively, and then we've got x equals 1, x equals 2 and x equals 3, and plug them all into the calculator, and there's our 0.0908 is our probability that x is less than 4. Okay, now using the calculator, on the previous slides we looked at kind of how we go about doing it in a kind of longhand mechanical way of churning out all the numbers and then cranking the handle and plot them all into a calculator, but as you can see that can be quite a laborious thing to do. So with the calculators that we've now got, this is much more straightforward. So we've got those two main Casio models. We've got the ClassWiz, which is kind of the more basic one, and then you've got the CG50, which is the graphical one. And what you need to do is make sure that you spend some time with your teacher knowing exactly how to get at all the values, because all those binomial calculations are in those two calculators. They are slightly different. This one, the ClassWiz, you can put the values in and get it to do an equal to or less than, which is actually fine. This one will actually do greater than ones as well. So for this one, you might need to do a 1 minus. With this one, you can do it the other way around. The other advantage of this one as well is that it will do it between two values. So you could, for example, do x between 3 and 8, for example. And again, it's like all the values from the binomial calculations, they're all in there. It does it all for you. Back in the good old days, even pre-calculators, you used to have to look these things up in these massive great statistical tables. Those tables still exist in the back of your formula booklet, but I can't imagine a situation where we're actually going to need that anymore. But they are there. But if you've got one of these two calculators, that makes the whole thing a whole lot easier. And the other thing to mention is that in the exam, whereas it used to be you'd get maybe 2, 3, 4 marks for actually doing a calculation by hand, now because examiners know that you've got the calculators that will do these things for you, that some of the calculations might only be worth maybe 1 or 2 marks, and a lot more of the marks now in the stats papers are for interpretation and understanding the context, which comes back to what the first part of that previous question, that part A saying why it was that our example to do with sleep patterns of students was actually binomial. Okay, if you want to have a look at those things, if you kind of go online, you'll find loads of videos that will show you how to do all the functions that you need, so I'm not going to go through those here. Right, that said, let's move on and look at an exam style question. So we've got a bias spinner that can only land on certain numbers, and we've got a random variable x represents the number that the spinner lands on. And hopefully you might notice if you watched the previous video that this is a question that I used in my video on discrete random variables, and we've already done it. So you might be thinking, why the hell did it include it again? Well, in the previous video, I adjusted it, and we did part A, but I took out part B. And what you're going to find nowadays is, on these questions, that you get a question that's on discrete random variables, and this is one that's taken from an exam paper, and then it will kind of neatly segue from a probability distribution function into something that is essentially a binomial. So how is it that the first part is a distribution function, second part is binomial? Let's just have a little look at it. Well, in the first part, we used all the information up here to create our probability function table of probabilities. And this is just to do with a single spin. What is the chance that from a single spin that we land on each of the outcomes? Those outcomes are not all the same. Right? But if we go on to part B is changing that and saying, well, you know what, we're only going to say that we want this spinner to land on a number 4. So the probability of getting a 4, that thing there, is going to become our probability of success. And we've now got 60 spins. So that's our number of trials. So we've got a fixed number of trials, which is 60. We've got probability of success, which is 0.35. And we want the probability that more than half the spins land on 4. So that's what makes it binomial. Since we've got fixed number of trials, 60, we've got successes, the spinner lands on a 4, so we've got p equals 0.35, and the spins are independent, so the probabilities are fixed. So that's how these probabilities are not going to change from one spin to the next. So what that gives us is a random variable, I'm going to call it x, is binomial, such that we've got 60, lost my mouse for a second, we've got 60 trials, and success is 0.35. And the probability that we want is more than half the spins land on the number 4, so we want the probability that x is greater than 30. Now, greater than 30, that's the same as 1 minus probability equal less than 30, so have a quick think about that one. If we want greater than 30, that means we've got 31, 32, 33, 34, and so on, all the way up to 60. And if we do that as a 1 minus, because 30 is not included in this one, we know 1 minus everything from 30 downwards. So thinking very, very carefully about those inequalities. And let's say if we try to do this by hand, you'd end up having to write out essentially a whole bunch, like kind of technically 31 individual calculations, each with 3 parts. So that'd be 93 separate bits plus all the adds, and it's just an absolute mess. But we've got our trusty calculator, so we can pick the number for this straight off the calculator, and there it is. And so that means the probability that x is greater than 30 is going to be 0.0589 to 3 significant figures.